A sudden call reaches Mozambique's presidential palace. The South African Air Force is requesting urgent clearance to fly through national airspace. An emergency? A threat of war? No, this was about a fish. The caller, Professor J.L.B. Smith, a marine biologist who'd spent over a decade chasing something most scientists believe didn't exist. And now, there it was. A 5-foot-long, 120-pound fish, iced and waiting. A species thought extinct for 65 million years. Its name, coelacanth, a prehistoric fish pulled from the deep in 1938, thought to be a one-time anomaly. But Smith believed otherwise. He believed this was a survivor, not a relic, not a fluke. A creature that had somehow endured Earth's most catastrophic changes and lived to tell us what the oceans once were. And it isn't alone. Across our oceans, living fossils still roam, unchanged for hundreds of millions of years. What do their bodies remember that our science has forgotten? Can these ancient species reveal how prehistoric oceans looked, moved, and functioned? And could unlocking their biology help us understand not just the past, but the oceans of our future? To find the beginning of this story, we have to go back, long before 1938, before dinosaurs, even before the first forests. Back to a time when the ocean was full of strange creatures. Amidst the craggy peaks of the Canadian Rockies in British Columbia, a series of gigantic dark shale formations line the mountainside. The layered rock contains one of the most vivid geological memories of a time in Earth's distant past. Within them, the remains of creatures that lived nearly 500 million years ago are entombed in rock. The shells and exoskeletons of creatures long dead are preserved in exquisite detail. In some exceptional cases, the impressions of gut contents and muscles are visible in the rock. This is the Burgess Shale, a rock formation which contains what many consider to be the most important fossils in the world. The Burgess Shale fossils originate from the Cambrian about 530 million years ago. The Cambrian world looks very different from our own. Smothered by a greenhouse, gas-rich atmosphere, the glaciers of the last ice age melt. A deluge of water follows. The many arms of the sea extend outward, submerging the lowlands of scattered land masses. The flooded earth appears lifeless at first. It's rocky and barren, as plants have yet to evolve and take root on the prehistoric surface. The restless land is volatile and prone to erosion, sending rocks tumbling into the oceans. Despite the hostility of the land, the early oceans teem with life. A soft-bodied trilobite, one of the earliest ancestors of modern-day crab or insects, ambles along the seafloor. In the ancient seas of the Precambrian, early soft-bodied animals reminiscent of mollusks or jellyfish drifted through the water. Towering, frond-like creatures resembling today's sponges swayed gently in the current, extending their frond-like appendages to feed. Disc-shaped creatures roamed the vast plains of viscous bacterial mats that blanketed the sea floor, grazing in quiet communion with the primordial depths. For the trilobite and its contemporaries, the serene rhythm is about to be disrupted. Just beyond the horizon, an evolutionary tempest brews, poised to transform their tranquil existence forever. the trilobite's peaceful day is interrupted. Rocks from the surface crash into the water, narrowly missing the trilobite. A plume of sediment billows upwards, and dirt swirls in the current, mixing into the seawater. While the trilobite avoided being crushed by the incoming rock, it unknowingly interacts with the catalyst for a biochemical revolution that will change its descendants' lives forever. The ancient waters are awash with calcium and phosphorus delivered into the ocean by the erosion of continental land. With these minerals, the soft-bodied trilobites begin to undergo a profound change. Using the free-floating calcium and phosphorus, they build. Squishy exteriors are covered by hard shells, ridges, and plates. But trilobites are not the only ones building. All around them, life forms emerge with complex exoskeletons, a multitude of jointed limbs and segmented bodies. Where once most animals would drift in the currents or crawl along the seabed, creatures scuttle, crush, dig, and grab. The idyllic stillness of the ancient oceans is no more. The Cambrian waters are a cacophony of limbs, jaws, claws, and myriads of other inventive appendages. With their new limbs, animals burrow into the once undisturbed sediment. They stir up long-buried nutrients which are rapidly seized upon by photosynthetic algae. The algae proliferate. Increasing photosynthetic activity changes the Earth's atmosphere and suffuses it with oxygen. Metabolic pathways evolve to take advantage of oxygen as fuel. Now, animals can perform the energetically costly work of hunting each other down. Enter the first predators. Their descent upon the ocean is visible in the fossil record. Unfortunate fossilized creatures bear the evidence, marred with bite marks and crushed shells. The Cambrian explosion ignites a desperate evolutionary arms race. New forms erupt in a frenzy of innovation, wildly diverse body plans, intricate structures, each shaped by a primal struggle for survival. Soft-bodied trilobites, vulnerable and unarmed, evolve into hardened survivors. Millennia of torment drive them to adapt. Each mutation a scream against the jaws and claws closing in. Some shield themselves with impenetrable armor, while others bristle with vicious spines, daring predators to strike. It's a relentless battle, each creature striving to outpace its own extinction in a chaotic, unending surge of life. Trilobites are just one of many groups that diversified wildly in the Cambrian oceans. The fossils of the Burgess Shale stretch the limits of human imagination when they were first described. The spiky hallucigenia was named as such because its prominent spines and spindly legs were so perplexing that its discoverers thought they must be hallucinating. The most infamous giant predator of the shale, Anomalocaris, was over 3 feet long, its segmented body covered in hard carapace. Its grasping appendages and stalked compound eyes were often the last thing that many an animal saw, as they were preyed upon by one of Earth's first apex predators. The Cambrian is the backdrop for all modern animal life today. All major lineages of animals that exist today emerged during the Cambrian, though most had not yet evolved the entire suite of traits that we use to classify them. Fossils like those in the Burgess Shale offer a glimpse into the origins of modern animal life and the incredible diversity of complex forms on Earth. But there's even more to discover. And so, to understand how vertebrate life truly began, we follow the first to carry a backbone beneath the waves. Amidst the spike-bearing worms and many-eyed arthropods of the Cambrian, one small animal is easily overlooked. It's about the length of a finger and almost completely transparent. Its ribbon-like body undulates through the water, barely making a disturbance as it passes by. This is Pichea. While it looks unremarkable, it represents a lineage that will shape life on Earth for the next 500 million years. What type of animal do you think Pichea resembles? When it was first discovered in the 1900s, scientists thought it was an odd-looking marine worm. But in 1977, paleontologist Simon Conway Morris controversially asserted that Pichea was, in fact, a chordate, the lineage from which all vertebrates, and eventually humans, arose. Superficially, you might think that you and Pichea have little in common. But if you're standing or sitting upright right now, the anatomy that allows you to do so has its origins in Pichea's. Pichea's body was supported by a notochord, a flexible rod-like structure that runs down the length of the body from head to tail. You don't have one now, but you used to as a developing embryo. In you and most other vertebrates, the notochord develops into the structure keeping you upright, your spinal column. The vertebrae of your spine can't do that alone without the help of the clusters of muscles supporting them, a trait also shared by Pichea. The curious zigzag markings running along its body are distinct bundles of muscle, a characteristic structure for chordates. Within the fossilized imprint of Pichea, we see echoes of our own body, the vague blueprint of something still in the process of becoming. In his book, Wonderful Life, Stephen Jay Gould dedicated the epilogue to Pichea. Deeply moved by the unpredictability of evolution and the contingency of our own existence, he wrote, "Pichea is the missing and final link in our story of contingency. Wind the tape of life back to Burgess times and let it play again. If Pichea does not survive in the replay, we are wiped out of future history. All of us, from shark to robin to orangutan. And so, if you wish to ask the question of the age, why do humans exist? A major part of the answer must be because Pichea survived the Burgess decimation." Stephen Jay Gould, Wonderful Life, 1988. The first scientists to discover the Burgess Shale fossils thought them to be so strange as to be alien, utterly distant from animal life today, let alone humanity. Today, we know that evolution connects us like a distant song, its rhythm manifesting in our shared anatomy and physiology, genes and biochemical pathways. Perhaps that's why we find ourselves so fascinated with living fossils. They are biological memories, storytellers of our past that hew as close to the original tale as possible. Wanting to understand where we come from is a very human impulse, and to understand it through creatures that look so dissimilar to us is both seemingly paradoxical, but strangely fitting. After all, the bodies of living fossils connect us to the vast panoply of life on Earth, even through vast swathes of time and space. Our origin story was never going to be ours alone. Let us trace the tale of our own evolutionary history, one major evolutionary transition at a time. we'll follow the lineage of the Cambrian chordates, branching through manifold forms of vertebrate life until evolution bears vertebrate life from the ocean onto land. The history of life on Earth has taken many strange, wonderful, and terrifying forms. At every juncture, a living fossil will be our guide. With their guidance, even the strangest forms of life will begin to resonate. The beat of your heart in perfect time with the primordial thump of its precursor. More in common than different. All connected as collective movements in evolution's symphony. All life forms on Earth simply variations on a theme. And within the intricate molecular patterns that act as the basis for the myriad forms of living creatures, deeper connections still wait to be uncovered. It begins with the emergence of the earliest vertebrates, the first fish. The first vertebrates were the jawless fish of the Cambrian, of which only 2 lineages survive today. One of these descendants will be our first guide, and finding it entails heading to the muddy depths of the sea floor. A word of warning, it might be a little macabre. Our first guide seeks out the dead. In a sense, it's appropriate. Seeking out living fossils to understand our origins means that we begin at the end. The carcass of a dead whale lies at the bottom of the seabed. Large predators like sharks have already bitten through its thick skin and ripped chunks of meat from bone. Remnants of blubber and sinew still cling to the carcass's now visible ribs. From within the whale's exposed body cavity, a creature moves sinuously, its long, thin body coiling around itself. Its scaleless grey-pink skin sags and droops, sitting loosely on its body like an ill-fitting sock. It contorts its slender form into a knot, tying itself around a piece of whale flesh, and uses the leverage from its own body to tear off a piece. It bores into the meat face first. 2 crescent-shaped cartilaginous plates protrude from its mouth, hinged down the middle and lined with 2 parallel rows of pointed teeth. But the creature does not bite down. It has no jaw. Instead, the plate of sharp teeth rasp at the dead flesh, scraping the rotting meat from bone. Nearly blind, it relies on its excellent sense of smell and touch to feed, drawn to the rot of carrion and the vulnerable tenderness of soft tissue. This animal is a hagfish, and it's a living fossil that will tell us the story of the earliest vertebrates. The hagfish, along with its sister taxon, the lamprey, are the last living members of the jawless fish. Together, they're known as cyclostomes, which translates to circular mouth, referencing their disc-shaped tooth plates. While the hagfish uses its circular mouth to feed on soft flesh, lampreys lead one of 2 divergent lifestyles. Carnivorous lampreys are parasitic, using rows of concentric teeth to bore into the flesh and blood of other fish. Conversely, non-carnivorous lampreys do not eat at all, surviving on the reserves from their filter-feeding larval form. As the survivors of their lineage, cyclostomes might suggest that all ancient jawless fish resembled bottom-dwelling hermits clad in formless, leathery robes. Their extinct counterparts did not necessarily share their lifestyle. The Devonian oceans over 400 million years ago were the renaissance of fish form. Ostracoderms, or shell-skinned fish, donned elaborate helmets, thick, often flat plates that covered their heads. The many shapes and sizes of their regalia are preserved in the fossil record, streamlined to resist strong currents, shovel-like to dig a quick hiding place, or embellished with sensory patches along its wide, fluted edges to sweep the seafloor for food. These valiant fish were only a few inches long, but bravely ventured into a variety of aquatic environments, from shallow coast to open water, though, like knights in shining armor, they no longer exist today. The last group of Devonian fish were the placoderms. The earliest jawed fish, their heavily plated head and neck acted as both defense and offense. Some of the largest specimens are up to 20 feet long and 4 feet wide, the siege towers or battering rams of the Devonian seas. Unlike other jawed vertebrates, they don't have teeth. Instead, an array of bony plates adorn their jaw, sharp and piercing like a pike, or blunt and crushing like a club. Their imposing armor gives the impression of heavy machinery, with a gap between the head and neck acting as a hinge. This allowed them to move their head upwards as their weighty lower jaw swung open, giving the deadly contraption of their bite even more force to pulverize their unfortunate prey. Compared to their extinct cousins, cyclostomes may seem like evolutionary oddities. Yet in their strange forms lie glimpses of the first vertebrates, a memory woven into their very anatomy. The notochord, mostly lost in adulthood, is retained in hagfish and lamprey. Instead of gill arches, the curved structures that support the gills in most fish, their gills are contained in muscular pouches. While most fish have paired fins, cyclostomes do not have fins on the sides of their body, only their midline. Finally, and most obviously, hagfish and lamprey, with their circular mouths, do not possess a 400-million-year-old trait, a jaw. While having a jaw might seem mundane, its evolution opened up a vast array of possibilities for vertebrates. Jaws granted the ability to bite down and secure prey. They were a highly customizable tool. They could be loosely connected and unhinged to swallow prey whole, or attached to powerful muscle to increase bite force. They could be long and thin, or dense and wide. With the support of tissues and membranes, they could be adapted for other purposes like communication, vocalizations, song, and eventually speech. Vertebrates were no longer limited to being humble filter feeders. The gnathostomes, or jawed vertebrates, were some of the most adaptable active predators the planet had ever seen. But how could evolution seemingly conjure a brand new structure from thin air? In the 1800s, the biologist Ernst Haeckel made a series of controversial drawings of embryos. Whether fish, amphibian, reptile, or mammal, Haeckel noticed that an early stage of embryonic development was remarkably similar. Every embryo had tiny folds along their neck, the pharyngeal arches, that resembled the gills of fish. To Haeckel, our fish-like embryos pointed to a fish-like ancestor. Haeckel had made an important observation, but interpreted it far too literally. Our embryos do not resemble fish embryos because we were once fish, but because evolution is excellent at repurposing existing material, especially during embryonic development. As the last bearers of our jawless ancestral inheritance, studying hagfish or lamprey might give us insight into how vertebrates evolved new traits. If you look along the side of a lamprey's body, you'll see 7 small openings, one for each gill pouch. If you examined the equivalent anatomy in a zebrafish, you'd find not 7, but 5 gills. But as embryos, both fish have 7 pharyngeal arches. In the lamprey, all the arches contribute to forming gills. In zebrafish, only 5 do. Instead, the first arch develops into the jawbone, and the second becomes a set of bones that suspends the jaw from the skull. Jawless fish show us that jaws evolved from the same structures as gills did. Evolution simply used the same components in novel ways to make different body parts. Think about your own face. You probably wouldn't say you resemble a hagfish or a lamprey, but the structures that develop into your facial anatomy originated with the common ancestor you share with them. As in jawed fish, the pharyngeal arches in the human embryo form parts of the jaw. But instead of gills, they go on to make much of the bones and cartilage of the skull and the muscle and nerves of your face. The face that you see in the mirror today was shaped on a deep molecular level by the same processes that once formed the gills of Cambrian fish. The gentle breeze passing over your face comes from air once siphoned through Cambrian gills, a quiet echo of a world long submerged. From those ancient breaths emerged the foundation of a journey that would push life beyond the oceans and into uncharted realms. As you can see, the story of the history of life is one full of parallels from start to end. They're shared even in the most bizarre of its tellers, ones that began crafting their own variations of the tale from very long ago. Our next living fossil is one of those tellers, an eccentric which has held fast to its tale since the next evolutionary transition within the jawed vertebrates at the very beginning of the evolution of cartilaginous fish. Old medieval maps used to indicate unexplored territory full of dangers, with drawings of mythological monsters, giant serpents, winged dragons, thrashing sea monsters. But our next guide was named after a monster. Instead of a marker of the unknown, it will illuminate the way forward at this next juncture, where cartilaginous and bony fish diverge. Our guide's namesake is referenced by the ancient Greek poet Homer in the 8th century epic, the Iliad. A thing of immortal make, not human, lion-fronted and snake behind, a goat in the middle, and snorting out the breath of the terrible flame of bright fire. Like Homer's monster, our second guide seems to defy classification. If you only saw it in parts, you might think each belonged to a different animal. Though not quite of immortal make, they are one of the oldest lineages of animals alive today. In Homeric epics, heroes sail over the wine-dark sea, but our next living fossil dwells in its very depths. It's one of the ocean's oldest ghosts. Gliding through the water, it beats its wide pectoral fins as a bird would use its wings to fly. Large, sea glass green, translucent eyes sit atop a bulbous snout, complete with nostrils. The rest of its body stands in sharp contrast, elongated, graceful, ending in a whip-like tail. Its odd teeth might seem more familiar in the mouth of a rabbit or rodent, blunt, flat-edged bony plates, nothing like the rows of serrated teeth in a shark's jaws. Visible lines and pores run across its face, as if they were seams holding together a composite creature. In the darkness, It glows like the pale fire of the moon. Our second guide is the chimera, one of the oldest living lineages in the world. Though it superficially resembles a shark, chimeras diverged from the ancestors of sharks and rays over 400 million years ago. In contrast to their prolific diversity, far fewer groups of chimera survive today. Most of them haunt the deep sea, up to 10,000 feet below the surface. Like an artist using a predecessor's technique, this elusive storyteller tells a tale about how life in the deep may have provided genetic mechanisms to shape life on land. Like the poems of antiquity, the history of cartilaginous fish is preserved in fragments. Their soft cartilage bodies rarely fossilized, leaving only teeth and scales. Just like their appearance, the story of their evolution also seems visibly stitched together, an unlikely patchwork made up of gills, embryos, sharks, and even a hedgehog. Trust an animal like the chimera to piece together these disparate elements and make a complete tale. Of all the chimera's curious anatomy, the most distinct difference between them and other cartilaginous fish are their gills. Most cartilaginous fish, such as sharks and rays, have 5 to 7 external gill slits. Chimeras have a single opening, covered by a structure called the operculum. With well-preserved fossils of ancient cartilaginous fish few and far between, shark paleontology was plagued with a decades-long debate. Which gill anatomy came first? Let's take a closer look into this mystery. Both the gills of sharks and chimeras have gill rays, structures that extend perpendicular to the gill arches to support the gills. Sharks have gill rays on 4 of 5 of their arches, but chimeras only have gill rays on the first. Like exploring a city built on the foundations of ancient ruins, perhaps looking into their construction would reveal traces of what came before and what came after. The developing gills of a fish embryo is perhaps the last place you'd expect to find a hedgehog, but this is no ordinary hedgehog. This hedgehog is a gene, the vertebrate equivalent of a gene first discovered in fruit flies. Flies with hedgehog mutations grew bristly, spiky hairs resembling the spines of a hedgehog. Vertebrates have multiple copies of the hedgehog gene, each thematically named for a type of hedgehog. 2 are named for species of hedgehog, desert and Indian, but the last, and the one found within these developing gills, was named for a rather different variety. Discovered by scientists with a penchant for video games, this gene is known as sonic hedgehog, blazing through these still-forming gills to help them take shape. In the developing gills of sharks, sonic hedgehog is found in all of the gill rays. In chimeras, it's found in rays extending from the first arch. But a tiny speck of expression is also found where the rays should be on the other arches. Each dot of sonic hedgehog forms a tiny bump of cartilage, the vestiges of a gill ray. This living fossil provided important evidence to complement actual fossil evidence that the chimera had evolved its strange gill anatomy from something that resembled a shark's. No matter how changed, each structure in evolution still retains clues to its origin. Variations of the tale of how the chimera lost its gill rays are told throughout the animal kingdom. Snakes and whales have vestigial limbs, with remnants of a pelvis as evidence that they once had legs. Certain species of lizards have fewer toes than their 5-toed, closely related counterparts. In the telling of all these stories of appendage loss, sonic hedgehog is the common thread that weaves them all together. By shortening the time or reducing the area in which sonic hedgehog is active, these animals have, like the chimera, reduced the size or number of various anatomical outgrowths. As with any influential master of their craft, the chimera's manipulation of this genetic technique is seen far and beyond its original creation. Compared to over 30,000 species of teleost fish, non-teleosts number only around 35 species. Gar, as well as sturgeons, beach ears, bowfin, and paddlefish make up this motley assembly of lineages, which evolved from 275 to 400 million years ago. Even before evolutionary relationships within fish were mapped out, Charles Darwin referred to gar as the original living fossils, noticing the distinct anatomical differences between them and most other modern-day fish. Just 2 centuries ago, colossal gar and sturgeon ruled the freshwater lakes and rivers of North America. The indigenous people who lived on the plains surrounding North America's Great Lakes, the Potawatomi and Ojibwe, recount how, when sturgeon returned to the waterways of their birth to spawn, rivers were so full of sturgeon that you could cross them by stepping on the backs of giant fish. Along the banks of the White River in northeastern Arkansas, curious visitors begin to gather. They brought an inventory of cameras, explosives, and even a machine gun. Though the waters are still, many treat the blue-green waters with trepidation. These are old wetlands, lined with cypress trees over 1,000 years old. It's 1937, and these people have been drawn here by the wild claims of Bramlett Bateman, a nearby plantation owner. For weeks, local fishermen had failed to reel in a good catch, and Bateman insists he's seen the reason why. The tranquil waters of the White River conceal a giant monster. Bateman claimed the White River monster had the skin of an elephant, 4 or 5 feet wide by 12 feet long, with the face of a catfish lolling on the surface of the water. Others came forward to say they'd seen the monster too. A fisherman described a grey-skinned creature as wide as a car and 3 cars long that he'd seen in 1915. And a woman named Ethel Smith reported seeing a terrible-looking thing with dingy grey-crusted hide while vacationing in the area in 1924. Sightings of Whitey, as it came to be nicknamed, continued into the 1970s. The consistency of the descriptions suggests that eyewitnesses were seeing a real animal, but what animal White River monster truly was remains unclear. Our third guide, however, is a strong candidate. The alligator gar lived among the last of the dinosaurs in the Cretaceous over 100 million years ago. It was once plentiful in the brackish waters of North America, lurking in the bayous and swampland of the US South and Southeast. With its blunt, broad snout and sharp teeth, its face would not be out of place on a prehistoric saurid. Gar is the Anglo-Saxon word for spear, an apt description for the elongated body and head of this grizzled survivor. Covered in dark, mottled chainmail garb, diamond-shaped interlocking scales made of super hard enamel, it certainly has the monstrous constitution to be the White River monster. Perhaps the ultimate testament to its sheer resilience is the discovery of a fossilized alligator gar just inches away from the KPG boundary line. The KPG boundary is a thin iridium-enriched layer, evidence of the meteorite impact that triggered the Cretaceous Paleogene extinction. The impact's most well-known casualty were the dinosaurs. Having gone extinct, their fossils do not reappear after the KPG boundary. The fossils of survivors reappear with distance from the boundary, indicating how long it had been since the impact. The return of large vertebrates especially was thought to have taken millions of years. But the 4.5-foot fossil specimen showed that the alligator gar was thriving, having recovered from the impact that killed the dinosaurs only a few thousand years later. Though it might be difficult to imagine today, massive gar and sturgeon thrived in the freshwater lakes and rivers of North America just over 200 years ago. Despite being consummate survivors, the 1800s brought on an onslaught of environmental pressures that sturgeon and gar were not prepared to face. Large and slow-growing, many live to be decades, if not over a century old. They usually reproduce only once every few years and can take 10 to 30 years to fully mature. Within 200 years, colonization and industrialization nearly did what a meteorite impact could not: drive them close to extinction. When European settlers began commercially fishing for herring and trout, sturgeons were notorious for ripping through their nets. Seen as pests, sturgeons were killed indiscriminately, their bodies dried and used as fuel to burn for steamships. Sturgeon eggs were sold as caviar in the 1880s, and the exorbitantly priced delicacy led to massive overfishing. The largest female fish, which could be carrying hundreds of thousands of eggs, became prime targets, endangering the sturgeon's future. Within a matter of decades, their ancestral waterways were drastically changed. Gar spawned when heavy rains flooded the low-lying plains of river deltas and bayous, an event that might only happen a few times in their decades-long lifespan. The construction of dams and levees sank water levels, cutting gar off from their historic spawning sites. Wrongly blamed for eating game fish like bass and trout, gar were deemed trash fish and killed in large numbers. So hated for their supposed lack of value that the Director of Research of the Texas Game Fish and Oyster Commission, Colonel J.G. Barr, built the electrical gar destroyer in the 1930s. Barr sailed the destroyer, a small boat rigged with a 200-volt generator and an electric net, along Texan waterways, killing 75 gar and 1,000 turtles on its maiden voyage alone. For decades, gar and other non-teleost fish were vilified as monsters or pests. The American blues singer Booker White once described the alligator gar as not one of God's creations like you and me. In an ironic twist, genome sequencing revealed that the gar genome bridges teleost fish genomes and our own. Most well-studied fish genomes belong to teleosts, such as zebrafish or ricefish. Where you might have one copy of a gene, a zebrafish might have two. Teleosts diversified and evolved rapidly, even duplicating their genome in the process. Mutations, losses, or changes in function or location of genes accumulated quickly, masking similarities with tetrapod genomes. Gar genomes evolved much more slowly and did not undergo duplication, making the task of finding the equivalent genes in a gar and a human genome more straightforward. Genes once thought to be specific to fish or tetrapods were found to have shared origins in our common ancestor. From genes responsible for choreographing our immune system's responses or fine-tuning the circadian rhythms of waking and sleeping, the gar teaches us that much of our fundamental physiology has a common origin with those of fish. The prospect of finding ourselves on the cusp of our own arrival in this evolutionary story might be exciting, but it was a major point of anxiety when it was first proposed. When Charles Darwin first suggested that apes and humans might share a common ancestor, there were many reactions of disbelief amongst 19th century intellectuals. The geologist and Reverend Adam Sedgwick, who had taken Darwin on his first geological expedition, feared that it would debase humanity, saying, "Humanity would suffer a damage that might brutalize it and sink the human race." With such strong pushback to the prospect of being related to apes, one can only imagine the level of abject horror our last living fossil would inspire in Darwin's Victorian England. It is a lobe-finned fish, the fish lineage most closely related to the tetrapods, the four-limbed vertebrates from which we are directly descended. Unlike Sedgwick, not everyone regarded our shared origins as a point of anxiety. The Gubbi people, who are indigenous to Australia, long regarded our last living fossil, the Australian lungfish, as an important part of their cultural cosmology. From an interview with elder Eve Fezzi, the Dreamtime or creation story of Dala, their name for the lungfish, goes as such. Many years ago, there were no animals on the earth. The Earth Mother and our ancestral spirits looked down and decided that they wanted to have animals, which would be their children. So they designated that Dala would first get a lung, then vertebrae, and then be able to walk, and that it would be the forefather and foremother of all the animals in the world. At the bottom of the babbling streams and lazy rivers of southeastern Queensland, the Australian lungfish whiles a sunny afternoon away. Its long, heavy body is deep olive green and brown, with large scales and a head shape more reminiscent of lizard than fish. It's mostly still. The lungfish is not in a hurry, first because it can live for over a century, and second, because it has perfected the art of endurance. If the scorching Australian summer reduces its habitat to a stagnant pool, the lungfish, as suggested by its name, can use its single lung to breathe air. The sounds of its inhalation are compared to the blast of a small bellows, a loud interruption to its otherwise relatively soporific existence. The lungfish is part of an elusive lineage called the lobe-finned fish. Only 8 species survive today, 6 lungfish and 2 coelacanths. Like coelacanths, lungfish share their characteristic muscular pectoral fins. The fins of most fish are soft tissue stretched over thin, bony projections. In contrast, the pectoral fins of lobe-finned fish are supported by fleshy, limb-like projections with an internal skeleton. In the Australian Dreamtime story, the lungfish spawns along shallow riverbanks so that its progeny can walk onto land, becoming the first land animals. Even before coelacanths were rediscovered as living animals, their fossils were fascinating to scientists for this very feature. Their fins attach to their body much like our limbs are to ours and could be used to walk along the bottom of the seabed. Some scientists speculated that the coelacanth could be a transitional form. Like the lungfish in the Dreamtime story, the lobe-finned fish was seen as an evolutionary transformation in process: fin to limb, fish to four-legged land dweller. The coelacanth, being very much alive today, was not literally the transitional form scientists were searching for. But according to the fossil record, such forms should exist. Over 350 million years ago, early tetrapods made the first fateful steps from water onto land. But what would a fossil suspended between fish and land dweller reveal to us? There was one aspect of the lungfish's Dreamtime story that proved incisive when searching for this ancestor. to find where animals first took to the land, search along the shores of shallow water. At first glance, the glacier-covered rocky shore of the Canadian Arctic would not seem like the appropriate place to look. Humbled by frigid temperatures and punishing wind and rain, scientists explored Canada's Ellesmere Island in search of the first land-dwelling fish. During the Devonian, Ellesmere Island was located very close to the equator. Instead of stark, rugged terrain, it was covered in lush greenery. Giant ferns and horsetails burst forth from the ground, surrounded by pools of balmy, shallow water. It's in waters like these that you might catch a glimpse of an ancient lobe-finned fish surfacing to take a breath of air. How would we know this Devonian fish was making the evolutionary transition to land? Is there a movement that might be characteristic to early tetrapods? Walking, or perhaps crawling, might be an obvious first guess, but it isn't either. Instead, it's the ability to do push-ups. You might be wondering what evolutionary scenario would ever prompt a Devonian fish to do push-ups. It isn't about doing push-ups per se, but having the anatomy that makes them possible. The next time you do push-ups, you too can experience the evolutionary innovations needed to bring our ancestors from water to land. First, think about the starting position for a push-up. Your shoulders need to support your body weight. As your elbows bend, notice that your arms are moving independently of your head. Unlike fish fins, your arms are attached to a shoulder girdle that's separate from your skull. Finally, as your body reaches its lowest point, you might feel strain on your wrists. Your hands are pressed flat on the ground, flexing your wrist joints, a structure that most fish do not possess. In a small stream, not unlike the ones that the lungfish live in today, a sudden disturbance breaches the surface of the water. A Devonian animal, pushing upwards on robust fins, erupts upward. Its large, crocodile-like head gulps air as it pulls the muscular upper half of its body out of the water. Almost 10 feet long and covered in scales, the creature looks like a fish, but its powerful fins can support its hefty body weight. It's surprisingly mobile for such a large animal, scrambling along mudflats and riverbeds. This is Tiktaalik, the Devonian lobe-finned fish uncovered on Ellesmere Island. The original fossil was strikingly well preserved, revealing that, unlike most fish, Tiktaalik could probably do a push-up. In the biting cold of the Arctic desert, the fossilized fish was nearly pristine. It preserved a distinct shoulder girdle, separated from the head of the fish. The substantially sized bone was well equipped to bear the animal's body weight. All the equivalent bones of the arm and parts of the wrist were present, with a functional shoulder and elbow joint. Even the rudimentary wrist joint could flex, allowing its forefin to bend. With its mobile, jointed fins, it could push its head out of the water to breathe air. Even its hind limbs were well supported by a pelvis the same size as its shoulder. Tiktaalik was not yet living on land, but like the story of the Australian lungfish, looked like its descendants could simply walk out of the water. Lungfish might not be able to walk out of the water, but they can do the next closest thing, walk in the water. This gives us an impression of how this evolutionary transition might have occurred in the distant past. Unlike their Australian counterparts, African lungfish have reduced their fins, making them appear much less robust and muscular. And yet, its seemingly scrawny pelvic fins can be used to propel them forwards or upwards and are capable of an array of movement. By using both fins at once, it could bound forward like a rabbit. By rotating its fins and placing alternating fins one in front of another, it could walk with a diagonal gait, similarly to a crocodile. Sheltered from the full pull of gravity underwater and buoyed by the air contained in its lungs, the tiny fins of lungfish were surprisingly capable. This upended traditional ideas of how walking must have evolved after vertebrates arrived onto land. Instead, all the motions for walking might have evolved underwater. Tracks thought to be left by ancient tetrapods may in fact be the work of walking fish. This observation could only be made in a living animal. With static fossils, it would be difficult to conceive of such versatile movements using such skinny fins. The lungfish understands that a good storyteller brings a story to life. With the momentum of its powerful fins, it leaps off the page from our underwater origins, showing us how evolution landed us in our terrestrial present. Living fossils are often seen as relics of distant geological epochs. Compared to the 300,000 years that modern Homo sapiens has existed, they have had a tenure on our planet orders of magnitude greater than ours. In some ways, they embody forms of ancestral life, reminders that we are comparatively fresh-faced newcomers. From another perspective, however, they are also reminders that we, along with all other living animals today, carry the same genetic history within our bodies, only in less immediately recognizable ways. Neil Shubin, an evolutionary biologist who was on the expedition that discovered Tiktaalik, wrote of evolutionary change, "Feathers did not arise during the evolution of flight, nor did lungs and limbs originate during the transition to land. What's more, these great revolutions in the history of life, and others like them, could never have happened otherwise." Major changes in the history of life didn't have to wait for the simultaneous origin of many inventions. Massive change came about by repurposing ancient structures for new uses. Innovations have antecedents that extend deep in time. Nothing ever begins when you think it does. Neil Shubin, Some Assembly Required, Decoding 4 billion years of life from ancient fossils to DNA. Just as fossils are imprints of living history onto rock, living fossils allow us to see the imprints of that same history on our own bodies. Like walking beside a stranger, humming a song we didn't know we had forgotten. Maybe the tune isn't quite what we remember, or maybe the tempo seems different in places. But we find ourselves humming along all the same, sharing an old memory in that fleeting moment where you walk side by side, the sound of your footfalls in time with one another before your paths diverge. Be sure to watch the next episode here, and if you want to unpack this episode again, save it to your YouTube playlist. Some journeys are better traveled twice.